Valeen Cobos and David Karan, and we are doing the solar-powered water filtration system. Our problem that we're trying to solve is that there are an estimated 700 million people in the world who don't have reliable access to clean water. Fortunately, that's a very large percentage of the population, and we aim to fix that. The water that they do have is not exactly the cleanest water always. Oftentimes, these are areas that are in war zones or just impoverished areas, and the water is full of microorganisms or debris. So that's a problem. And a 2015 global risk study showed that this is the #1 risk to society as a measure of devastation, because there are so many people in this danger zone of not having water. And so that's our motivation. To fix that, we want to raise the number of people. It's not all doom and gloom. The number has been rising. In 1990, there were about 4.1 billion people in the world who had access to water, to fresh water, to clean water. And in 16 years, that number raised to 5.7 billion. So it is on the rise, but we would like to increase the rate at which people have access to this water. So we're going to do this by way of creating a system that can deliver up to 70 gallons per hour to a family of 4. This system will be powered using green energy, the solar panel, charge a battery. And the system will run for as long as there's sun. We're aiming for an average of 6 hours a day, and for that to charge a battery that can run up to 3 hours. So a total of 9 hours running time per day, spread between daylight and nighttime, or overcast conditions. The system is also aimed to be deployed in Haiti, where there is a much needed need for water because of all the terrible conditions there. The set of standards we're going to use to design the system are, namely for the pump, we're going to be using the International Organization of Standardization, the ISO 17613. Namely, that deals with the centrifugal pumps and their removal of water from bore wells, both shallow and deep bore wells. Specifically, the separation of water from sand or from suspended particles within that water. As for the filter, we will be using the NSF 53 or 58 rated reduction removal filter. This is a filter recommended, or the standard recommended to remove all but viral components within a set of water or liquid. Unfortunately, there exists not any filters that can remove viruses as they are very, very small, so we will do the best that we can. As far as encompassing global awareness and global learning, we want to make this system as affordable as possible. We want a very low-cost system that can be deployed anywhere in the world. We're aiming for Haiti, but you could use this in Africa or in India or in Southeast Asia. These places are oftentimes also need water, so we will make it affordable to them. As a result of these places that have a low income, oftentimes it goes hand in hand with their literacy rates. In Haiti, for example, they have the lowest literacy rate, 55% in the Western Hemisphere. This is a problem, so what we need to do is place the burden of knowledge upon ourselves, the designers and developers, and make it easy to use for them. Very user-friendly. And here's Alan.
Good morning. My name is Alain. I'm going to be talking a little bit about the components that we're going to be using in the system. We divided into primary components and secondary components. For primary, we got the solar panel, the water pump, filters, the batteries, and the charger controller. For secondary, we got the casings, piping, strainers, and cables, little stuff that we may use later. What is a solar panel? Well, as we all know, it's a device that is made to harvest the energy produced by the sun, and to convert this energy into electricity. They are made of photovoltaic cells, and the way it works is that they capture the photons emitted by the sun, and released by sun, yes. It is a clean energy, it has no emission, it got no moving parts, and it can be used or it can be placed anywhere where there is sun available. The water pump is another device that is made to move fluid by mechanical means, and it's going to be important for system since it's going to be the only source of power to move the fluid around. There are different kind of pumps, and some of them are designed for a specific task. The filters is primarily used for removing unwanted materials or foreign objects. For water purification or the LSH, they are going to be essential for removing bacteria that are capable of providing illness to humankind. Typically, they're rated in microns, and the smaller the rating, the better they are to filter bacteria. Here we show you a picture of a human hair, so you guys can see how a micron is pretty much the size. This is a human hair of 50 to 70 microns. The big one here is about 30, 20, 10, and this small one, little dot, is about 1 micron. And it has been proven that that filters rated for 1 micron or less are capable of removing 99.99% of bacteria found in water. Some of the formula that we're going to be using are this one that shows here. Pretty much is about electricity and fluid mechanics. We got the following: power, Ohm's law, conservation of mass, and Bernoulli equation. In Bernoulli equation, we're going to be using the Moody diagram to find the Darcy friction factor and maybe the pressure loss and head losses that we may encounter in the system.
All right, thank you, Alan. My name is Devinder Puran. I'm going to be presenting to you the design alternatives for our system. At the heart of our system is the centrifugal pump as the first design alternative. And the centrifugal pump is comprised of these components. You can see here the impeller, expeller, multiple casings, liners, and coverings. And at the heart of the centrifugal pump itself is the impeller. The impeller is responsible for the centrifugal force that draws the water through the system and is then expelled with the expeller. And the current goal of the system for the centrifugal pump is to improve upon it. And we plan to do so by optimizing the impeller blade, which is shown here. So continuing with our second design alternative is the diaphragm pump. The diaphragm pump is usually applied in the oil and gas field where they extract muddy water with it. The diaphragm pump is not as capable as a centrifugal pump, but it's a viable option if need be. And here you can see the SolidWorks model as well as the multiple components within the diaphragm pump itself. So diaphragm pump's not as capable, so right now we're leaning towards a centrifugal pump. Furthermore, how are we going to prove one pump is better than another? So we plan to create the whole pump along with the other components in SolidWorks and later on export them to either Smoothly Abacus, ANSYS, computational fluid dynamics, or SolidWorks flow simulation. So the idea is, continuing here, we want to recreate the impeller, and we want to use one of these means to do so. There are multiple ways to create an impeller, and once you create the impeller, you can then run a flow simulation on that impeller. And some of the methods used to create are the circular arc with a forward or backward curve, or the point-by-point forward or backward curve. As you can see here, there's a flow simulation ran in SolidWorks from our research. And you can see once a certain flow simulation is ran on it, you can see which pump impeller is most efficient for that system. And the end goal is to take that impeller and improve upon it and use less power and get more water output.
So when we put together all the components and the designs, alternatives, we come up with a proposed design. And our proposed design is we want to use the solar panel, and that will charge a battery. The battery will then run a pump, and the pump will draw the water up through a hose or a pipe system, through a filter, and be deposited within a water storage reservoir. We have a basic overview here. This is the system that we want to put together. Not necessarily looking like this, but this is the flow chart of what we want to do. So in the coming months, well, what we're going to do is follow our timelines and division of responsibilities so that we can put this together. So what's next is that we will finalize our component selection. We will create these models in SolidWorks and do the simulations. Once we are set upon which are the optimal pieces to use, we will begin assembly, manufacturing, and designing and finishing up our impeller design. And that's it.
Thank you. Any questions for the team?
Yes, sir.
Yeah, I don't know if you're aware of this. There's a TED Talk. You're familiar with TED Talks? Just on a filter, microfilter for cleaning water or dirty water right from the dirt and to put it in there. It's pretty cool. You should look it up. My question is, why 70 gallons per hour for a 5? How do you come up with that number?
Well, 70 gallons per hour is based on the American family of 4 that uses about 400 gallons of water a day. When you compare that to the amount of water used in a developing country, the United Nations recommends between 15 and 50 liters per day, which is about 5 to 20-ish gallons. So what we want to do is, with 70 gallons an hour, we say enough for a family of 4. It's enough for an American family of 4, but this will be more than enough for a.
But my understanding is that that's for drinking water or that's for everything?
It's for drinking. It's for dishes,
Okay,
cleaning.
good. All right. Now you were saying you were trying to look for a 5% increase in the impeller design
Yes, sir.
for your pump. Have you determined what actually is the limiting factor of your process? I mean, is your filters going to be a 5% increase in performance of your pump? Will it make any difference if your filters are the ones that are preventing the flow?
Well, we are looking at the main bottleneck of our system would actually be the power draw from the battery, because the solar panels may not provide enough power, and so we don't want to overdraw.
Yeah, but I'm looking at the fluid wise.
Oh, the fluid,
Yeah,
yes.
because I'm not talking about performance. You're talking about a 5% improvement on your pump impeller at the same time. I'm not sure if that makes any difference in your design aspects of it when you're having a microfilter with 1 micron, getting muddy dirt going through that filter.
Well, the actual filter itself will have a grate on the front of the hose to prevent any large items like.
So it's going to be a stepwise
Yes.
system while it goes all the way up to the final 1 micron will be actually virtually clean water.
Correct.
All right, I mean, that wasn't clear on that. And I'm sorry, everybody else, I'm sorry, I got a few questions on this because it's pretty interesting. Now, I didn't see you compare any alternatives to that technology.
With technology-wise?
Yeah, I mean, solar power, instead of making electricity, what about using just solar heat to boil the water and condense it somewhere else? You can't, obviously, you're not going to get 70 gallons an hour with that, but you could collect it for a while. I mean, I'm not sure, I'm just thinking if you have alternatives, and your water source is going to be what, the ocean, salt water?
It'll be a lake, but more likely a bore well. So
A what?
a bore well.
Wells.
Okay.
Yeah, the design alternative we wanted to focus on was the pumps. That we figured that would be the heart of our system, the main
Yeah, I mean,
component drawing the water.
the positive displacement pumps usually is going to be a better source if you have muddy waters and all that. The impellers are going to be shot.
Well, these waters are typically not muddy. What the main limiting factor for drinking and consuming this water is
Bacteria and all,
correct, the pathogens.
Pathogens. So that's usually what you're thinking about. It's not that water you see in the TV with
Right.
a mud hole and that you're talking about.
Not middle safari, you know.
Right. I mean, that's what I saw when you guys were thinking that. So I'm done with that. Thanks. Good idea. But check out the TED Talks.
Have you guys looked, I know you mentioned earlier that it will remove 99.99%, but nothing to do with viral.
Right.
Have you looked at incorporating some type of antiviral aspect to this?
Well, when we looked at the standards from the Centers for Disease Control, the recommendation was really the only reliable way to remove viral components would be to boil and lye them.
Yeah, the filter are pretty much gonna remove the bacteria found in any water source. but it won't kill the virus
Right.
in the water.
Well, I'm thinking something along the lines of, since you are using solar already, either a magnifying aspect maybe in your reservoir, or you've got electrical there already as well, maybe some electrolysis, or something of that sort. Like I said, alternate forms, just as a consideration.
Any other questions?
Now, this goes back to your motivation. You said the 700 million lacking access to
Reliable access, yes.
and this came from a 2015 what?
It's
Global
the
report?
global studies report. It was in I believe it's the World Health Organization. I had it listed here. It was, yeah, World Economic Forum. Yes.
Okay, all right. And you say you're going to fix the problem?
No.
Oh,
We wish we could fix the problem. We want to alleviate the
But
problem.
you stated that. You said that.
Oh.
So, okay, so
Well,
we're
I
going to
think-
create a system that can help alleviate the
Yes.
problem. That's what you want to say.
Ideally, we could fix it, but I don't. I think that's beyond the scope of our abilities.
May I see the next slide, please? In that second paragraph, you talk about 5.1 billion to, I'm sorry, 4.1 to 5.7. Can you give me an idea of percentage? That's an aggregate number. Are we going backwards or forwards percentage-wise?
We are going forward because the population in 1990 was about 6 billion, and in the intervening 20 years, we've gone about a billion.
Thank you. Next fall, read your slides better. You've got a lot of grammar and punctuation errors. Okay?
Any other questions? Well, thank you very much.
Thank you very much.